Before we do number 10, I'd like to remind you the definition of a critical number. The critical numbers for a function f are those numbers c in the domain of f where f prime is equal to 0 or where f prime does not exist. So to find the critical numbers, it's the derivative equal to 0 or the derivative does not exist. So let's take a look at this next one. For the function below, find the critical numbers, the open intervals where it's increasing and decreasing. So our function this time is f of x equals x plus 3 to the 4/5. Now, since this function is an odd root, just as a reminder, this means the 5th root of x plus 3 to the 4th power. And you can take an odd root of both positives and negatives. So this is anything from negative infinity to positive infinity if it's an odd root. Now, if it's an even root like a square root, you can't take the square root of a negative, but this is an odd. So since our root's an odd, that's that denominator of the exponent, there are no restrictions on the original domain of this function. Let's see what happens when we take the derivative, though. So let's see. F prime of x is the power 4/5 times the base x plus 3 to the power 4/5 minus 1. And I'll go ahead and do the chain rule here, but the derivative of x plus 3 is 1. So this becomes 4/5 times x plus 3 to the minus 1/5. That's 4/5 minus 5/5. It's minus 1/5. So that negative exponent is going to force that base to the denominator. So it will be 4 over 5 times x plus 3 to the 1/5. And that means 4 over 5 times the 5th root of x plus 3. Now, earlier I said that you can take the 5th root of any number, and that's true. Except this 5th root occurs in a denominator. And so this denominator can never equal 0. So we've got to find out where that would be 0. Well, 5 times the 5th root of x plus 3 would be 0 if x is negative 3. So this is actually a critical number because this is a value at which the derivative does not exist, and it's in the domain of the original function. So remember, your critical numbers have to be in the domain of the original, okay? And then they're where the derivative is equal to 0 or does not exist. So since that original domain was all real numbers, that means our derivative does not exist at where that denominator is 0, which is negative 3. So we've got to put that critical number on our number line. So now I will test my derivative, f prime at negative 10 and f prime at positive 10. So when I substitute a negative 10 into 4 divided by 5 times the 5th root of negative 10 plus 3, that gives me 4 over 5 times the 5th root of negative 7. That's perfectly fine. You can take an odd root of a negative. It's some decimal. If you wanted to do that in your calculator just to see, you put negative 7 to the 1/5, but you need parentheses around both the base and the exponent. But it would show you that that's just a negative number. And the actual value doesn't matter. This just means that our derivative at negative 10 is a negative. So in this first region, from negative infinity until I reach negative 3, the derivative is negative. That means the function is decreasing. When I substitute a positive 10, 4 over 5 times the fifth root of 10 plus 3 is 4 over 5 times the fifth root of 13. This is some positive number 4 divided by some positive number 5, fifth root of 13. This is going to be a positive. So in the region from -3 to positive infinity, the derivative is positive, therefore the function is increasing. So we have one critical number, -3. The function is increasing from -3 to infinity and decreasing from -infinity to 3.